Okay, so hello everybody. Today the seminar is going to be led by our colleague, Jesús Maíz. So we all know him, but as a summary of his trajectory, he got his PhD in 1999 at the Universidad Complutense de Madrid. And after that, he's been at the Space Telescope Science Institute, first as a postdoctoral fellow and then as an ESA staff astronomer. He came back to the Instituto de Astrofísica de Andalucía with Ramón y Cajal in 2006, and he has been with us at CAP since 2014. His scientific interests are everything about massive stars, their formation, environment, the membership to clusters or associations, and the larger scale galactic structures that they belong to. So today he's going to tell us about Gaia. So thank you very much, Jesús, for being here, and whenever you're ready.
Thank you, Maria. Thank you for the introduction, and thank you everybody for coming. So today I'm going, as the title says, I'm going to be talking about Gaia. And let me see if this works. Okay, let me wait. Okay, yeah. Okay, so this is a summary of the talk. It's going to have basically three parts. First, I'm going to be giving you an introduction to Gaia, the mission, the instruments, and the timeline, and look at how the Milky Way looks in 3D thanks to Gaia. And then in the second part, I'm going to be there's a lot of science that has been done with Gaia, so I'm just going to be very brief. I'm going to give you the greatest hits of what has been done, because there are many papers published since they started to become available. And then in the last part, I'm going to show you the work that our group is doing with Gaia. So in a nutshell, Gaia is a science mission that is studying the Milky Way. And the goal is to analyze over 10 to the 9 stars, and doing this with 3 types of data: astrometry, photometry, and spectroscopy. With astrometry, we get very precise positions. We also measure distances, or to be more precise, we measure parallaxes, and from there we infer distances, and proper motions, which are the motions of the stars in the plane of the sky. We also do photometry. Depending on how you count them, there's 1 or 3 bands, because two of the bands are actually spectroscopic, but right now the only information we have is photometric about those. And then the third leg of the information is the spectroscopy. From a spectroscopy, we can derive physical properties and measure radial velocities of the over 10 to the 9 stars. So why is Gaia important? What makes Gaia different from other missions? Well, the most important thing is the number of targets. It has over 10 to the 9 targets, and this is several orders of magnitude more than what any other previous mission has studied in terms of astrometry. But not only there are many more targets, is that the precision and accuracy is much higher already. I mean, from the data releases we have right now, and it keeps increasing. So if future data releases will be even more precise and more accurate. And not only because of the astrometry, but because of the combined information. I'll give you some examples in this talk, how the combination of astrometry with photometry and later on spectroscopy gives us really too much information. At this point, one of the issues we have with Gaia is how to handle how much information we have to process. So I'm going to start the talk with an official movie from ESA, and this is in here. You're going to see an animation of how the mission was launched. So it was launched from Kourou in 2013 with a Russian rocket. And here you see how the simulation. Here you start to see how the spaceship was still attached. And here you see traveling towards its destination, which, as you'll see in a moment, is in a L2 position. Here you see how it is unfolding. And what you see there unfolding, it actually has 2 things. First of all, they have the solar panels, which are used to power the spacecraft. But that circle you see in there, besides having the solar panel, it also acts as a heat shield. And one of the reasons why this happens is because Gaia has to be very, very stable. And that stability requires it being shielded from the sun, and also requires that you see this Lissajous orbit around the L2. Purposely, it avoids the shadow of the Earth, and that is done so that it has a very high thermal stability. And as you see, Gaia is observing in 2 directions simultaneously, and it's sweeping the sky. And here you have in this animation how it sweeps. Basically, it has a precession, and thanks to that precession, it covers the whole sky. Okay, so here the animation is finishing. Here you have an aspect of what I was telling you before. So here you see that Gaia observes in 2 viewing lines that are separated by a basic angle of 106.5 degrees. And here's the direction pointing toward the sun and the rotation axis of the spacecraft. And this has a precession in 63 days, right? So it keeps observing in this continuous trap of observation. And that is one peculiarity. Gaia observes continuously. It doesn't stop. And you'll see this, that it has a curious design for the CCDs to do this. So how does it look like? Well, for those of us who work here at CSIC, the answer is very easy. It looks like the thing that is in the front of CSIC. We have a one-to-one model, and we see it every day. So it's no secret of how it looks like. But in case you want to see it in reality, here, you see it in before being launched, and here you have a person. And well, then again, this looks like the model we have in the front. So again, so here you have, this is where the light enters, and they have 2 mirrors, and then deflects that to the detector. And here you have what acts as a heat shield, and the solar panels are on the other side. So this is the focal plane. Now the focal plane is huge, and you have the dimensions. Here is 104 centimeters by 42 centimeters. So, so this is this is a sizable size of the telescope. And the interesting thing is that here you have the different CCDs. This is the part where you do the astrometric field. So this is where you get the positions and also the G-band photometry. Here you have the blue photometer and the red photometer CCD. So this gives you low resolution spectrophotometry. And here you have the radial velocity spectrometers. So the way this works is that, remember, this is continuously moving. So this arrow tells you how much a star moves in 10 seconds. Okay, so you see that it takes less than 10 seconds to cross one of these CCDs. So a star keeps moving like this continuously. First, you have these CCDs that are used to detect the stars. Then it goes through the astrometric field, then the blue photometer, the red photometer, and finally the radial velocity. So how this works is that the CCDs work in a continuous transfer mode in which the charge is transferred from pixel to pixel at the same time as the star is moving, and then is collected at the end. And in this way, it has several advantages. Basically means that it's a continuous mode of observation. It also means that you have kind of an automatic flat field, because there are actually many physical pixels involved in the detection of a single star, basically because it's moving this way. And then, again, the information is collected here at the end. So the 2 coordinates, instead of being 2 spatial coordinates as in a typical CCD, the 2 coordinates are space and time. They are always collected here. So this is the spatial coordinate, and time is because you keep receiving photons all of the time. The other interesting aspect is that there is definitely too much information here, meaning that it's not possible to send all the information, to send all the charge detected as a function of position and time. And this is true by actually a couple of orders of magnitude. So what is done is that there is a software on board that collects the charge and compresses it, basically just takes the light around the detected stars and sends it to the ground where it's processed. And this requires a lot of processing that is done by the team, and then this is produced in the form of data releases. Now, here you have a timeline. I start with saying Hipparcos because Hipparcos was the predecessor mission. That, of course, this was done 30 years ago. It it was incredible at that time, but of course Gaia is so much better. Gaia was launched already 7.5 years ago. And the first data release was in 2016. There was a second data release in 2018. And then it was decided that the third data release, there was already too much information to be processed in time. So it was split in two. First, the early data release was released in 2020, and the third full data release is expected for 2022. And what happened here was that only part of the information, for example, the spectrophotometry, meaning that what you see from the blue and the red photometer detectors, that will only be released in 2022. What we have now in 2020, from last year, is the information from those detectors, but collapsed in wavelength, meaning that what we have now are 3 bands, G, B, and R. Now there is a nominal mission. The nominal mission originally was just for 5 years. So the nominal mission started in 2014. So it will cover the period from 2014 to 2019. And the data release for data for that nominal mission was is going to be in 2024, 2025, but that original 5-year mission has already been extended until 2022, and it's possible that it would be extended until 2025. Why do we need more years, a longer mission? Well, there are several reasons, but I mean, can be summarized in 2. First, for things like parallaxes, basically getting more data, more epochs, give you better accuracy. But the point in which the information gets significantly better with time is with proper motions, because proper motions, as you'll see now, it requires seeing how the star moves year after year. And here, extending the baseline increases what you can see by a very important factor. So how do you measure distances? Well, what you measure actually is parallax. And this is probably, you've seen this many times, but the idea of parallax is you have an object and you want to see how far away it is. So you look at it from 2 points of view. And by looking at with a distant background, you see that the motion of the object with respect to the background changes. So when you see it from here, you see the star in front of blue. And when you see it from here, you see the star in front of red. So and the closer the star is, the larger the movement is. And that works in our case by, here we are, this is the Earth moving around the sun. And if you're observing from here in June, the star looks to be in this direction. And if you let 6 months go by, it has changed. Now, this is the basic theory. Reality is a lot more complex than that, because what you see here is you have a background, right, that you can establish as your reference. When you do the data, this is not really what happens. In the end, you can actually establish this background, for example, with quasars, but it's something that is done a posteriori. It's not something that is done during the processing. And this is the reason why, if you remember, Gaia is observed in 2 directions at the same time, with a basic angle of 106.5 degrees between the 2 of them. And what it's doing is, by observing these 2 positions at the same time, and then doing a lot of processing once the data is on the ground, it does the trick of using those 2 positions as a trick to convert this from a relative to an absolute motion. And well, I mean, there is a lot more complexity to that. But here you have a summary of the difference between parallax and proper motion. So parallax, the effect of the motion of the Earth around the sun, gives you an ellipse. It means that if you observe a star throughout the year, it moves like this. And the amplitude of this amplitude is a function of basically how far away the star is. And the ratio between the axes depends on the position along the with respect to the ecliptic. But at the same time, the star is moving because it has a motion, a proper motion. And what you see in the sky is a combination of the 2 effects. It's the ellipse plus the straight line. So you see something like this. Now, if you see now this, how it looks like in reality, this is a field in which you have stars at different positions, and each one has a different trajectory, right? So you have one is being drawn, but you see that the other stars, all of them move. So like this one that is moving, this has a very large proper motion. That's why it moves so fast. The ones that you see the circle is small, is because they have a small parallax. If the circle is large, you have a large parallax. So once again, the trick here, let me put this again, so you can see the movie again. The trick here is actually you go star by star, and for each one of them, you have to deduce the proper motion and the parallax. The information is combined, and there are two issues here. One is that, as you see, is that the longer you wait, the more years you let go by, the longer the effect of the proper motion is larger. So that's definitely one advantage. Let me put it again. But another problem that you see here is that which is which. So this star is moving. So what you have is a number of large individual positions, and you have to be able to assign a given identity to the star. You have to know which is which. And this is not trivial. And there are a number of false positives, false identifications. And one of the magic of the processing of the data is that you're actually able to do this. And of course, there are mistakes, and this gives rise to objects with bad solutions. But the nice thing is that the longer you wait, which means the larger number of months you have, or in terms of data releases, the higher the data release, the confusion is reduced again and again. So for example, the data in early data release 3 has a much smaller number of issues with this type of identifications than DR2 had. So this is a reconstruction, because remember that Gaia actually just gives you positions and magnitudes of how the Gaia looks as the galaxy looks as seen by Gaia, right? So this is just the image, and here you see the galactic plane, the large Magellanic Cloud, the small Magellanic Cloud. If you look a bit more, you can even see a few more galaxies and globular clusters. And here you have a reconstruction. This was not done by the Gaia team, by somebody, another team will actually combine Gaia data with something else. So this is the galaxy, and this was actually with DR2. So this is not the most up-to-date, but this is a simulation of how to the region of the galaxy that is explored by Gaia. So you see several things. So you have, this is the region around the sun, fine. This is the galactic bulge, and with the bar, right? And there, those are a number of bright stars, and this is a significant population. And let me actually go put this again. And you can see other things as you turn around. You can see the Magellanic Clouds, for example. They are quite obvious when we turn around. So there you have the Magellanic Clouds. You have a few other objects that seem to be far away, and some have galaxies, some are globular clusters. And you see this structure that looks like fingers. And these fingers are caused by a combination of two effects. The first one is that you have regions that are hidden by dust. So you have a point here, maybe dust, and basically this blocks what is behind. You'll see this more clearly in a while. And the other reason you have these elongations is because, and you can see perhaps more clearly in the case of the Magellanic Clouds here. Of course, the Magellanic Clouds are all, one is here and the other is there. And this is the LMC, this is the SMC. By the way, this thing in here is 47 TUC. That's a globular cluster in front of the SMC, and it produces this type of structure. So what happens here is that this elongation is the uncertainty you have. And how to deal with this uncertainty, of course, is another issue, but the point is that a given object, especially if it's as far away as the LMC, which is about 50 kiloparsecs away, will be a spread. This spread is much smaller, of course, for objects that are near us. You'll see this also in another one. So that was in 3D. If we look in 2D, this is how the galaxy looks. This is actually DR2 data, but it hasn't changed much in EDR3. This is the density of sources as a function of galactic coordinates. So this is galactic longitude and latitude. What do you see here? Well, you see the galactic plane, where most of the stars we see in the galaxy are. And as you go away from the galactic plane, you see fewer stars. Some of these objects, some of these things are, or these are structures that have to do with the way Gaia sweeps the sky. And as these are two, you could still see them in future data releases. They will not be there. So you also see here the galactic bulge, fine. You see, of course, these two are the LMC and the SMC. They are the most notorious things you can see of the galactic plane. But what are these? Well, these are dust clouds. These are clouds that are more or less in the foreground, meaning, well, you can, if you want to have a value, typically they are around 1 kiloparsec. Most of the objects you see here are probably 3 or 5 kiloparsecs. So the moment you see a dust cloud, it blocks the way of seeing what is behind. And you see these are minima. You can see the effect here because this is the average color. So you see blues are blue stars, red are red stars. So for example, you see the Magellanic clouds are basically blue stars. They are, most of other stars are, you see they are main sequence or not highly distinguished stars. But here's the interesting thing. So if you go between these two, you see there is a correlation. So for example, take this area here, okay? So remember, this is a dust cloud. So, oops, away. So you can see that in there, you have indeed a minimum in density because they are red. And the same thing, you can see the same type of structures in here. Okay. And this is the third interesting issue. This is the Gaia average parallax, the inverse of the distance. So what you see here is that, okay, so these are the objects that you see in the halo. There's a lot of noise. There's a lot of noise because there are few sources compared to the galactic plane, but the point is that they are all nearby. Most of these objects are, well, typically between 1-2 kiloparsecs, right? And you can see this in here in the values of the parallax. However, once you go into the galactic plane, you keep seeing deeper and deeper. And of course, if you go to the Magellanic clouds, they are about 50 kiloparsecs away. So they are, on average, the regions of the sky where you see the objects more distant. But what about this? Well, this again, these are the dust clouds. In these dust clouds, you have dust blocking you the way. So the objects there, the regions there, you see they are redder, fine, but they are, because basically what you see are the regions that are just as they are being obscured by the dust clouds, but it gets to a point where you don't see anything. And basically you are left with these objects that are maybe 1 to 3 kiloparsecs away, while the rest of what you see there is farther away. Now, let's talk a bit about how this how this relates to stellar evolution. So you can also do color magnitude diagrams, right? With Gaia, here you have, well, the typical structure, which you have temperature against luminosity. But of course, what we see with Gaia is this plot on the left, and here you have color against absolute magnitude, fine. I also plotted here on the right the same color, but here against distance. So to give you an idea, this is log of pi in milliards seconds. So this corresponds to about 1 kiloparsec. This corresponds about 10 kiloparsecs. Okay, so what do you see here? Well, first of all, you see a spread, and that's because this is the measured parallax, and there is just a spread. It's not actually, most of these stars that you see here are not that far away. They're actually here, and here you have the effect of the spread because of the uncertainty in parallax. But what is true here is that most stars we see in Gaia are in that region, which corresponds from the region from about 3 to 5 kiloparsecs, right? And of course, so that's the majority, the bulk of the objects we see in Gaia. And here, what you see on the left, you see several things. Okay, so this is what would be the main sequence if stars had 0 extinction. Fine. But stars have extinction. So these stars that you see here are actually objects in the main sequence, but the lines here you have shifted is what happens when you increase extinction. So these stars are actually in the main sequence, but they have some originally they were here, and due to the effect of extinction, they become redder and dimmer following this trajectory. And what you see in here are red giants. In particular, these objects in here are red clump stars, and these are from the red giant branch, most of them. And this extinction that you see is the effect of the red clump star, which, if there was no extinction, they will all be more or less around here. But this is the effect of extinction. And remember, we are seeing mostly in the galactic plane, so the extinction is considerable. There are other things that you see here. These are sub-dwarf stars, and these are white dwarfs. And in this case, they are usually nearby. They have low extinction. So in this case, they follow more or less the expected trajectory. Okay, so now what I'm going to do is I'm going to play a movie where we go through the galactic plane. Now, let me explain what you see here. So these 3 plots that you see here, these are just the region in the galactic plane. And they are the 3 plots I showed before. So this is the stellar density. This is the average color. And this is the average parallax. Okay, and here you have the scale in density, in color, and in parallax. And to help you, so right now I'm pointing at the galactic center, right? Fine. So this is the average longitude where we are. And to also help you, I'll tell you in which constellation we are. So this is towards Sagittarius, right? Fine. So, and what we see here are the same diagrams as before, but just for that region of the sky, okay? And so we start here. I'm going to play the movie, and you're going to see how this works, how this changes as we move through the galactic plane. And you see that things move. Why? Because you see that in the color magnitude diagram, it moves to the right and to the left. Sometimes it has 2 populations. That's because, well, different points you have different extinction. Now you'll see that in general, now we're going to have low extinction because we're moving up. This is the region of the sky away from the galactic center. But as soon as we move towards the galactic center, you see that in general extinction increases. But of course, there are particular directions in which extinction is higher or lower. And so you can see this. And I'm going to play the movie again. Now, paying attention to what we see here. On the right, you'll see different structures. So one thing I'm interested in is OB associations, which are blue stars. And you can see whenever you see a concentration here, is that we are in an OB association. Okay, so for example, that's an OB association. Very interesting one, another OB association. That's another OB association we just went through, and that was Carina, for example. And with this type of, so this is what I was referring to before when I said that Gaia has huge amounts of information. Here, remember, here we're combining color with parallaxes and with absolute magnitudes. So by exploring this information, and there are several ways of visualizing it, we can learn a lot about our galaxy. So this is the first part of the talk. This is a description of the kind of information we see with Gaia. Now I'm going to show you the greatest hits, and this is a very particular selection. This is the 3 things from Gaia early day release 3 that impressed me the most. Okay, so this is the first one. This is a study by Xavi Luri et al., in which they analyzed the population of the Magellanic Clouds based on Gaia EDR3, and what they did is they did a sophisticated selection algorithm to retain only the stars that belong to Magellanic Clouds, which is not trivial because of the spreading in parallaxes. And with that, they were able to do several interesting things. One of them, for example, this is in this diagram, this is the LMC and this is the SMC, the LMC and the SMC again. And they were able to see by doing the proper motion, something that had never been done at this kind of precision, that actually there is a flow of objects from the SMC to the LMC marked by these lines. And this is seen both in the young stars and in the old stars. Furthermore, another thing they were able to do is this is the LMC, and do maps for different populations like Lyrae, IGB stars, or different types of young stars. And see that actually, well, they follow different, they have different structures. Like, for example, the bar is clearly seen in these old populations, but it's not so clearly seen in the young populations, where recent star formation is has a more important effect. This is another very neat result, and this has an animation included. So what you're seeing here are the proper motions of quasars plotted over the whole sky, and they were able to see a very small effect that is caused by the acceleration of the solar system around the galactic center. So by doing astrometry, they were able to see that there is a residual component in the proper, remember, in principle, the proper motions of quasars, well, they are so far away that it should be very tiny, but the effect of the motion of the sun around the galactic center, they were able to measure the acceleration, and the value they get is consistent with what was known about the mass of the galaxy. So this was a very neat effect. And just to show this again. So basically the thing is that there is a very tiny effect. Of course, this is a clean diagram where the noise is not there, but this is the component using the vector spherical harmonics. And this is, again, this is what the residual effect they were able to see. And they measured that this pattern that points towards the galactic center. And this, as a third interesting result, they made a catalog of nearby stars, and you can see there in the abstracts that they produce over 300,000 objects and contains at least 92% of the stars of star type M9 within 100 parsecs of the sun. And again, this is a huge, very interesting catalog that can be exploited to many things. One of the things they do it, and this is really surprising, is that they detected something that I'm not an expert in the field, but I think this was not expected. They detect that in the color absolute magnitude diagram, there was a gap. And they named this the Yao gap. And this gap is produced by an effect in the stellar evolution that basically makes the number of stars be smaller than what you see in the rest of the main sequence. And again, this is something that can only be done when you have data that is of as good quality as you have in Gaia, and furthermore, in which you combine different types of information, such as color and absolute magnitude, for which you need parallaxes. And then for the last part of the talk, I'm going to give you a summary of the things we have done with Gaia, our group, and with and we're working on. So the first thing is we're studying runaway stars, and this was the first paper we published, and this was done with the help of my student, with Michelangelo Pantaloni, or Mickey for friends. And what we did is we did with the first data release, and is to look for runaway stars, meaning these are OB stars that have been ejected from the birthplace. This can happen either. There are two possible mechanisms. One is a dynamical interaction in a triple system or higher order in the center of a cluster. And the second mechanism is by the supernova explosion. And what you see here is this is galactic longitude, and in the two diagrams, and this is the proper motion in galactic latitude and galactic longitude. And there is a pattern that is following the two. And if a star falls outside that pattern, it means that it's moving with respect to the nearby star, and it's a runaway star. So with this study, we were able to identify objects that had previous detections, and some, like the ones that are marked with squares, the ones that were actually new runaways. So this was the first thing. Another thing we're doing is combining Gaia with ground-based surveys. In this case, this is an image we obtained with a ground-based survey from Teruel, which it's an observatory called Javalambre, and this is a survey which is called Galante. And this is a Galante image, and I'm going to do a zoom. This is an H2 region, and the zoom is onto the ionizing cluster that is producing all this nebulosity. What you see in green is actually H alpha. And what does Gaia give us? Well, what it gives us is something like this. This is the information we have from the ground. And with Gaia, we can do this. Meaning, this is a chart built from Gaia in which you have information on the magnitude by the size of the circle, the color from Gaia. And the other thing we have is these arrows, which are most of the times are small, but in some objects like this one and this one are large. and those are the proper motions. So what this tells us is that once we have the ground-based photometry, we can merge this with data, with Gaia data, and have even more information. And the nice thing about this is that this, once you know how to handle Gaia data, this is very, very thorough and very complete. You can you can do this cross match very easily, and you get cross matches of more than 99%. So that means that the Gaia data is very, very clean. Now, two more things that we're doing. We're actually doing calibration, which is boring to most people, I know, but it's necessary if you want to trust the data. Now, in this case, the DPAC, which is the group in Gaia that is the official group that does a calibration, does a calibration that is available once each data release. But I like to do my own calibrations, and this was not my original plan, but I ended up doing a lot of it. And I have been doing both photometric and astrometric calibrations. And this is the result so far. I published a recalibration of the G photometry for data release 1 in 2017. And then in 2018, I published also with a collaborator with Michael Weiler in Barcelona. I published a recalibration of the 3 photometric bands. So why do we need to do this? Well, we need to do this because Gaia has a very, very good precision, meaning the uncertainties we measure are very small, but there are some hidden biases that need to be corrected. Now, Gaia is so complete and so thorough that the information is clean, meaning consistent, but you need to correct these biases. So, for example, for data release 1, I discovered that the published sensitivity curve was not the correct one. So that was the first thing I did. And then for the data release 2, with this collaborator, what we discovered is not only that the sensitivity curves had to be redone, but actually there were corrections that had to be applied. And what you see there is our work for data release 1 and data release 2. We're now working on data release 3. So if you're working on it, I have to tell you that there are also corrections. And the published calibration can be improved. And we already have this done, and we're in the process of writing the paper. Meaning that in a few months, you will see on AstroPH something published that makes basically improves what has been done so far. So you have to stay tuned for this. In the same way, the astrometry can be recalibrated, and this is something we start doing for EDR3, and we published a paper here. This was just very recently published. In this case, the story is different. The calibration done by the DPAC team is very, 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 very good. And in this first paper, what we actually did is to validate it, not to correct for it. Meaning validate, meaning that indicate that it was actually with an independent data set test that it was very good, and estimate how to deal with the intricacies of correlations, transformations from internal uncertainties to external uncertainties, and that was it. So that was our first paper, and what you see here is the paper I'm currently working on. It's a follow-up, and what I have found in this paper is that even though for most stars, the official calibration is very good, for a subset, meaning bright stars, it's possible to produce a small improvement. I wouldn't say a large improvement, but it's a small, but it's significant, and means that the parallaxes for bright stars can be correct. And again, most of the correction was already done by the official calibration, but there is a small correction that can be added to that. And that's what I'm working on right now. Now, after calibration, now here we have results on scientific results. One thing that we're working on is on the Villafranca catalog of galactic orbit groups. And the reason for this is that even though the parallaxes for individual stars are very good, once you have a group of stars, meaning usually a cluster, but this can also be association, you can improve on the average distance by combining information from all the stars. And how to do this is a bit tricky because the uncertainties are correlated, and that was indeed part of the reason for doing the previous work on the astrometric calibration, is to estimate these correlations correctly. So last year we published our first paper on this catalog of galactic orbit groups using DR2 data, and what we're working on now is on an extension, reanalyzing the DR2 data with DR3 and using 10 new groups. And to give you an idea, what we do here, this is how we estimate the distances to a cluster, actually a double cluster, using Gaia data. So let me first draw your attention to the three top panels. Okay, these two are easy to interpret. These are two optical images of this cluster, which is called NGC 2264. And the reason why you see this blotch here is because it's an H2 region. So what you're seeing is basically nebular emission. Now, what you have here is the same region, exactly the same region. And what you have in the background is the Gaia source density with dark red, meaning large number of stars, and blue and yellow, sorry, meaning low density. And the blue stars are the stars that belong to the cluster. Now, first, is interesting thing. You see that the cluster is where the density is lower, and this is completely counterintuitive, right? Because a cluster is an object that adds more stars, right, to a foreground or background population. So how come is this? The reason is that this cluster is at a distance of about 700 parsecs, and the population here is a background population that is about 3 kiloparsecs. Now, the cluster has an H2 region associated with it, and the H2 region has not only gas, but also dust. And dust produces extinction to the background. So what you see is, okay, these are the cluster stars, and once you get beyond that, you see almost nothing, because the dust associated with the cluster blocks the view. So again, this is something that you can see that we can do this with Gaia data. Why? Because in addition to this, we also have the proper motion diagram. So this is proper motion in right ascension and declination. And you see here that the maximum, which corresponds to the background population, is very different from the cluster. Why? Because the cluster is close to us, and doing that, basically it's moving at with a different velocity with respect to the galaxy as the background. So you can see that we can use the information from Gaia to separate one from the other. These two plots here now, this is parallax as a function of color and magnitude. And what this is telling you is that, well, this is the cluster, and this is the background population, which you can see here is parallax, is farther away. This is about 1.3, which is the 700 parsecs, 1.3 milliards seconds, while this, on the other hand, is about 3 kiloparsecs away. And this effect, you can see it not only in color, but also in magnitude. Most of these stars that are actually here in the background are actually quite dim. They are between magnitude 18 and 20. The cluster, on the other hand, has lots of bright stars. And then here, you see the same effect. All of this is Gaia data. This is the color magnitude diagram. And you can see the cluster. This is the background population. And you can see how it traces an isochrone pretty well. Also, notice how these low mass stars are separated from the isochrone. And that's because these are pre-main sequence stars. So they haven't reached the main sequence yet. And finally, you have here the parallax as a function of number. This is a histogram, and this is normalized parallax, meaning the parallax minus the parallax of the cluster divided by the uncertainty. What you see here is that when you look at the parallax histogram, Most of the stars are here, which means low parallax or high distance. And this bump is what is produced by the cluster. So the cluster is just a small part of all the stars you see in Gaia. But once we have the selection algorithm, you can see that it has this nice distribution. These are the objects that have been discarded as not belonging to the cluster. And when you plot this in this normalized parallax, you see this is a logarithmic scale in the vertical direction. You see that it's a parabola, meaning that it's a Gaussian distribution. So our algorithm selects a very nice distribution of distances, of parallaxes in this case. And actually, and the one other thing we know is that it's a double cluster that has 2 cores and 1 halo. So all of this is what we can learn just from applying the information in Gaia. And the last thing I'm going to show you, the last result, is the catalog we're doing of OB stars in the solar neighborhood. So remember, the previous one was clusters or groups in general. So here we're going one by one, and this is the analysis that Mickey, my student, is doing. And this is what we just published, and we are calling this the ALMA catalog of OB stars because it's based on a previous catalog started by this person, Cameron Reed. Okay, and to show you what we're doing here, probably the most interesting result is we're using OB stars to trace the structure in the galaxy. So this is the galaxy looked from above. So the galactic center is here towards the right. And here you have the spiral arms, and you can see in purple the spiral arm that is closer to the galactic center is the Carina Sagittarius. Then is the Orion Cygnus or local arm, which is where we are. And this is the next spiral arm, which is the Perseus arm. Well, the one interesting thing we used to the Gaia to discover is that there is this structure, which we call the Cepheus spur, that is a kind of a mini spiral arm that is extending from our spiral arm towards the Perseus arm. The other nice thing about Gaia is that it has allowed us to calculate not only the position in respect to the galactic plane, but the height. So here you have the height of these stars with respect to galactic plane. And what you can see here is that the Cepheus spur is about 100 parsecs above the galactic plane. And again, this is what we published in this paper. And right now we are working on a follow-up paper. This was done with DR2. We're now working on data with EDR3. So this is my next to last slide. So to remind you that Gaia is a work in progress. So because it's the first time that about 10 to the 11 simultaneous astrometric, photometric, and spectroscopy observations have ever been processed. So results need to be calibrated. There is more data in future data releases because parallaxes and proper motions get better with more observations. And there is new data, spectroscopic temperature, radial velocity, variability, solar system objects, it's even the possibility of testing gravity models. And of course, if you combine this with other surveys like the one we're doing, Galante, or others like TUMAS, there's a possibility to do a lot more things. So this is the end of the talk, but for the questions, what I'm going to do is I'm going to leave you with a movie that Mickey, my student, has done. And this is a number of movies he has done. So what you have here are the stars you saw in the previous image, but now with much better positions because this is now done with EDR3 data instead of DR2. And here with the data, he has done this animation in which we are traveling towards the solar through the solar neighborhood, and we see different structures. Here we're just across the galactic plane. And here, for example, you can see how we go and see the Orion OB1 association, which is below the galactic plane, and then it goes and goes to other association, and then it goes to even to the older data. This is Cygnus OB2, and then it's going to give an animation in which it shows the different spiral arms as in the previous slide. So that's it. I can now answer your questions.
Thank you very much, Jesus. Very, very interesting talk. So if you have questions, please raise your hand. If you don't have a micro, you can write your questions on the chat and I will read them out loud. And I already see a hand raised, sorry. So if I can go ahead, please.
Thank you very much, Jesus, for this very nice talk. I was wondering whether you are contemplating any possible scenario to explain this Cepheus spur. What is causing the, that this feature is just going off the plane of the Milky Way?
Well, that is a general thing that is seen in galaxies, which is called a corrugation pattern, right? And it was kind of interesting because nearly at the same time we were publishing this, there was another paper that was detecting this using different techniques. And it's nice because it was independent confirmation. And why is this done? Well, it's probably the fact that the galaxy is a complex place, right? And so it's due to interactions with other objects. Now, I will leave that to theoreticians to do. The funny thing about this, I don't know if Mickey is listening, but he's going to laugh when because he thought I wouldn't dare to say this. But the nice thing about this is that Mickey is still doing his in Spanish estudiante de grado. He's still doing his bachelor, right? And this week, he has an exam on galactic extragalactic astronomy, and one of the topics he's studying is corrugation patterns in galaxies. So I told him, well, if they ask you this question, you should tell them, well, I have a paper about this.
That's nice. Not everyone can say that. Nice. And I have a second question, if I may. I was wondering whether you are for these regions that have extinction, if you pick one very well studied cluster, all the association where that it has also observations maybe in the radio, that these proper motions are also done in the radio. Is that something that could be done? This combination of
Yes, there are many things that can be done there. I mean, well, first of all, the problem here is that, what I said before, there is too much information, too many things to do, right? I mean, right now, if I wanted, with the data I have in hand, I could write 10 Gaia papers. I just don't have the time to do 10 Gaia papers at the same time. I'm doing just 3 at the same time, okay? 10 is too much. 3, I'm doing it. But anyway, yes, radio and other surveys. With radio, one of the things we did in the Villafranca 1 paper is to compare distances with masers, right? So, and one of the things we did is to compare with basically almost anything that had ever been measured to these clusters. And one of the things we measure are masers. And of course, the better agreement was with eclipsing binaries, right? Because that's very precise, and with masers. The problem with masers, the only reason why we have some discrepancies with masers is the complexity, meaning that some of these clusters are double or have some structure. So it's not clear whether the maser can be a bit behind or a bit in the front. So in some cases, you expect to have discrepancies, but other than that, it was that. But other things that can be done. I mean, extinction. Extinction is one of my favorite topics, and there is just so much that can be done with extinction, with this, right? And especially combining. My plan is to combine this with Galactic photometry. I have HST data to compare it with. I have another ground-based spectrophotometry, and there are many, many things. Now, with extinction, there is one thing. This is a warning. I was thinking about, I mean, since I didn't have more time, there was a slide, something that we discovered in the ALS paper, is that if you look at the Gaia papers, there is a lot about extinction published, right? So one thing we discovered is that these mega papers that have, I don't know, 10 to the 8, 10 to the 9 stars that combine extinction, most of them think that all the stars are red, intrinsically red. They are not obvious stars. And their conclusion is that the extinction measured to obvious stars using these algorithms are wrong. And I mean, we published, I mean, what the expected correlation was and what the published correlation was, and it was nonsense. So the thing is that, yes, extinction can be done and it can be done properly, but what has been published so far using Gaia and obvious stars is wrong.
Right. Good to know.
And again, this is in the paper. I mean, if you look at Pantaloni Gonzalez et al. 2021, you see that this and there is I mean, once you read the fine print of the papers, it makes sense. For example, I mean, the main Gaia DR2 paper that published extinctions said, oh, we are only comparing with or stars with models up to 15,000 Kelvin. Okay. So if the star is 30,000, okay, yeah, we're comparing with the one with 15,000. Well, of course, then the result is something else. I mean, because your model does not include that. And in other cases, you had even weirder things that there was one case, another paper basically considered that most OB stars in the sample had negative extinctions.
I see. Okay. Okay, I have a look at your paper. Thank you. Thanks so much.
Okay, there is a couple of questions in the chat from Juan Miró. So the first one is, how much better is the parallax precision in the early data release 3 with respect to the data release 2? And the second one is, how did you establish the stars that belong to the cluster, only by distance, or conversely, how did you discard field stars that do not belong to the cluster?
Okay, I can talk about half an hour for each one of these questions. Okay,
okay, do it.
They are very good questions, but really, I mean, I can give you a summary and tell you to go and read the papers because really it's a lot. But just to give you a quick problem. Okay, uncertainties. The main problem with uncertainties is that they are correlated. Okay, and first of all, you have that correlation introduces a systematic effect. Now, the systematic, so if you just take a look at the published uncertainties and you compare DR2 to DR3, fine, that's a simple answer. It's about, well, they are better by almost a factor of 2, okay? Probably between 1.5 and 2, okay? But interestingly enough, where the improvement is better is in the systematic effects. And that's why we wrote this paper, the one in 2021. And that means that there is the most important thing is that there is a systematic effect that cannot be corrected at this time. And our estimate for that effect in DR2 was about 42 microarseconds. And in the new data is 10 microarseconds. So it's a factor of 4 better, okay? So that's the biggest improvement. But how do you deal with the systematicity of those effects? Again, it's tricky and you have to read the papers, okay? Now, about how do you select the stars from clusters? Again, that's what I gave you, the example I showed you was the easiest example, okay? And you have to combine information. The information we do is positions, proper motions, and positions in the color magnitude diagram. And once we have done that, there are a few stars that have to be excluded because of the normalized parallax, meaning they are 10 sigmas away, and you expect a contamination, that's the last thing you get rid of. Now, the question is, what do you give more weight to? Positions, proper motions, or position in the color magnitude diagram? And the answer to that is it depends. It depends. You have to go cluster by cluster, start by selecting the stars that you know are a member of the cluster. They are the stars that actually define what the cluster is, and then work from there. And if, for example, if the cluster is nearby, meaning less than 2 kiloparsecs away, usually proper motions are the best thing. But once you get farther away, the problem you have is that the stars, the proper motions converge to a point. So proper motions become less useful, other than to eliminate objects in the foreground. So what you have to do in those cases is usually pay more attention to extinction. And what happens with these objects is that you usually have a higher extinction than the rest of the population. So you put an isochrone shifted by a given amount of extinction, and that way you selected. How do you do that exactly? Well, you have to try. I have an interactive code that basically allows you to play with the parameters, and with different parameters, so you have the issues of you include more and less stars that you know are part of the cluster and things like that. To make things more complicated, you have runaway stars. Meaning, what is a runaway star? I already explained in the context of the whole galaxy, but some of these clusters have ejected stars. And in those cases, you actually see them because they are objects that are at the same distance as the cluster or compatible with the same distance, but they are relatively far away and their proper motions point away from the cluster. Now, of course, this is, we call them candidate runaway stars. We're not 100% sure they are runaways, but they are the most likely explanation. So then you have to treat this separately. So in our papers, we actually go cluster by cluster and say, okay, this one has maybe 2 or 3 or 4 stars that are possible runaways. They need to be studied in more detail in the future to check whether they are runaways.
Okay, there is another question from Eduardo Martin. So how many unresolved multiplicity affect your results for OB stars? How many unresolved multiplicity affect?
Okay, that's another very good question. So there are 2 issues here to summarize it. One, what happens if what you're talking are closed binaries or well-separated binaries? So Gaia is able to separate, if the magnitude difference is small, Gaia will separate objects that are 1 arcsecond or farther away. Okay, so those are not, those you get 2 values for Gaia. If they are between 0.7 and 1, it depends. And if they are less than 0.7, chances are they are not resolved. Okay, so that's what you mean by unresolved. So if they are, on the other extreme, you have objects that are spectroscopic binaries, objects that are, okay, they are unresolved, but they are so close that the astrometric signature of the spectroscopic motion is very small. So in those cases, you can just forget about it. The problem are the ones that are relatively wide but unresolved. And that, again, that's a good question. And what happens there? The issue is that in some of those cases, they can be identified because the astrometric solution is of poor quality. And Gaia allows you to do this. And on the other hand, in some cases, they are not. And for the objects of interest, there's actually nobody who has done a thorough study of how this works. And we are the first ones interested in it, and it's on our to-do list to analyze. More specifically, there's this interesting question. What astrometry is revealing you is the motion of the photocenter. Okay, fine. What does this mean? It means that if you have 2 stars that are identical, it doesn't matter, because no matter how much these stars move, from the point of view of Gaia, the photocenter is always at the same position. So it's like they are a single star. If they are 2 stars of different magnitude, then there is an effect, but the effect is small because the photocenter moves, but not much. Now, what is the interesting case? Well, the interesting case is where the companion is a compact object, because in that case, you are tracing the motion of the luminous star, and the dark object, you don't see it. Again, this has not been, we have published a paper on one of these objects. We actually discovered that the astrometric quality is very good. So at least in this case, nothing is seen, which is interesting. But we have a pending study in which we are going to analyze objects with these characteristics and see what happens.
Okay. I can't see any more hands. I have a curiosity. So you mentioned that the Gaia mission can be extended until 2025. Mm-hmm. So is it thought that after that, the improvement in proper motion is not worth it, or is it just a question of budget? Or
No, the problem is there basically is that the spacecraft could not be controlled from that time on. There is a fuel aspect that needs to be used to maintain everything in place, and the estimate is that after 2025, 2026, so it will run out of the fuel, and then
okay.
I mean, it's not fuel. I mean, it's kind of something. Yeah, basically you shoot a jet of material and then you use that to control the attitude, right? But after that point, it will run out.
Okay. So
unfortunately, I mean, if it was a question of funding, I would even be willing to make a collection.
Yeah. Okay, thank you very much. Very interesting. And thank you everybody for being here. I will stop the recording.